bioinformatics.
Hi everybody, my name is Karim Sop and I am an assistant professor at Bioinformatics. I'm a computer science professor and I'm specialized in systems. So when we talk about systems, this is everything from the hardware until below the operating system. I'm going to talk about a topic that is very relevant to bioinformatics, but it is not the core of bioinformatics, or it's not technically within the biology and the science of bioinformatics. It's about operating systems and big data and how they affect bioinformatic execution of algorithms to make them better. So basically, first of all, how many of you is from computer science background? Oh, I'm going here. Okay. Good. So I think the rest, I'm not going to go deep into technical details of computer science. I'll try to be able, or try to, as much as possible, to cater on the application needs of bioinformatics. But I'm going to explain for you a main problem that if we don't solve quickly, we will have some sort of a hit wall that will appear at some point in time, because data is getting bigger and things are getting out of hand. So basically our main question that we're going to debate about today is, are current general purpose operating systems designed with big data in mind? This is a very important question. If you think about it, it's extremely important because it affects bioinformatics, it affects the execution of big data, and if we don't actually enhance our operating system, which most programs take for granted, we will not be able to speed up the execution and get better performance. Okay, so let's take an example in bioinformatics to be able to relate the two topics. Sequence alignment, for example. Sequence alignment is the use of computer search to do sequence alignments, string matching between DNA sequences and some sort of a database. So as the data set gets bigger and bigger, the problem gets complex, and we need to speed it up. So why we need to speed it up? Sequence alignment is an application for many other applications. It's kind of the raw material for other applications in bioinformatics. So those are kind of examples of applications that depends on sequence alignment, like genome assembly, for example, like genealogy, pathogen identification, taxonomical and functional classification. All of these are applications that depend on sequence alignment. So if we can enhance this example through some untraditional techniques, we can enhance those as well. But why we need to make it fast? So most of the people here will think about, or most of the audience will think about, we want it more accurate. We wanted more quality of results. Yes, that's true. But if it's slow, you will not be able to get the results in the first place. So basically NGSs, which are the next generation sequencers, are getting cheaper. They are getting cheaper, at the same time they are getting more powerful. They're getting more data. This stresses the environments for processing this data. We need to utilize our computational resources better to be able to account for that. Also, there are a lot of needs for fast response, like, for example, bioterrorism attack, viral mutation, for example. Things that need high response. When we talk about alignment, for example, sequence alignment, this will take days to align some reads to a specific database. Okay? So I'm trying to draw your attention from where you come from to get you where I want to talk about. So again, to our question, our current general purpose operating system that we take for granted to execute our alignment and our algorithms for bioinformatics and big data designed for that specific purpose, are they enough? Are they optimal? That's the real question. So to be able to answer that, we need to cover quickly some aspects of historical background about operating systems. Why we reach this status of general purpose operating systems, and why do we need to change them in this context. I'm not talking about the whole change of operating systems. General purpose operating systems are really very good for general purpose use. But for specific applications like big data and bioinformatics, we need to do some amendments. We need to do something about it. Okay? So at the history, operating system started as a program, custom-made program to run on specific hardware. It was designed like that. There was no real line between the system resource management, which is the role of operating system, and the applications that are running on top of the application of the operating system. So the hardware started to mature, start to get better and better, and people felt the need. Architecture designers, all the software industry, the whole software industry start to feel the need for isolating the operating system from the application, and then we came up with a new feature called operating systems that is responsible only for managing the resources of the hardware and allowing the applications running on top to get the maximum out. Okay? Then, it started to develop. This thing was a threat by itself. New stream of a software type. And through the history of operating system, we started with batch processing. So we had batch processing operating systems in the old days. And those were characterized by assigning the most precious resource of a computer, which is CPU, to a job that never leaves the CPU until the job is finished. So consider throughout the lifetime of this job will do I/O, will wait for events, will interact with the user. The CPU sit down there doing nothing until the job is done. If we have other jobs in the queue, they will wait until the job is finished. Then the whole arena of computer science starts to think about alternatives. How can we fix this problem? How can we utilize the CPU cycles to the full? So they thought about time sharing. How can we time share the CPU time? And the whole idea here is we need a solution for this kind of problem, and the solution came from the hardware architecture, with the introduction of what we call interrupts. How to interrupt the processor when we can take it to do something else while some process is sleeping or waking. And basically we have two types of interrupts or time sharing, the preemptive and non-preemptive. In the non-preemptive, basically you have a process that is running, and a mechanism was introduced for the process to leave the processor when I/O is needed. But the process will leave on its own. It will decide, which is really not nice. You cannot really time share the processor time effectively. Another introduction by the hardware to solve the problem more and make it more generic was to add what we call the timer. And this is the main concern that we're going to talk about today. This is what we're going to solve. A timer for an interactive applications environment is very efficient. It's a breakthrough. It's kind of going to the moon. Because it allows interrupting the processor and transferring control to the operating system, where the operating system can decide whether to continue with the same process or to switch to another process. And this gives more flexibility and more time share control. Okay? So we have those two models. Then we were faced with standardization and portability, all of these nice features that operating system designers start to think about. We want our operating system to be unified from the application point of view. I don't want to restrict my operating system to a hardware that I'm running on. So they start thinking about those features. Those features are very important general purpose operating systems, but they impose an overhead. They come at a cost. And this cost is basically deep stack. So if you are going to scale a database or a data management problem to run on a cluster of nodes, every component of the application will run on one node. Those components need to communicate together. They need to talk. They need to exchange messages. For one component to talk to another component, it needs to traverse the whole stack. That's an overhead. This whole stack was built specifically to provide interoperability, unification of interfaces, APIs, all of these. They are good, nice features, but they come at a cost. Then, the last thing that were introduced, multi-core architectures. When the ARM race, gigahertz, battle finished, you cannot increase the processor CPU anymore because of physical reasons, power dissipation, cooling, all this stuff, even the speed of light, the speed of electrons. You cannot do better. So architects in hardware start thinking about other alternatives. Multi-core, just put more cores. Don't increase the speed, put more cores to do more stuff. And in that sense, operating system designers start to think about ways to utilize the new environment, the upcoming new environment. And they have two approaches, and this is another core important point that we're going to talk about in the solution. We have two approaches, SMP and AMP. SMP stands for symmetric multiprocessing, where if I have multiple cores running within a single computer, all the cores within, or all the CPUs within this single computer are running the same image of the kernel, identical. And the other one is AMP, which is asymmetric multiprocessing, where you can group cores by role and give them different kernel images based on what they are going to do. Okay? Of course, operating system designers and manufacturers chose the first route because it's easy. You can port your application without doing a lot of change. But again, this comes at cost. You pay for this out of performance. Okay? What I'm trying to say here, so nobody misunderstands, I'm not trying to say that general purpose operating systems are bad. They are not bad. They are good. They are good for the sake of general purpose applications. But they are designed to serve average on all different application types. They are general purpose by definition, by name. They are not designed to work 100% efficient for databases, for example, or data management, or bioinformatics. They are designed to be fair for everyone. Give the resources in a fair manner. So back to our original question, after we have discussed this quick history. Our general purpose operating system designed with big data in mind? Actually, no. There are fundamental conflicts among scalability, shareability, and performance. And we are much interested in performance, but we're going to look at these two quickly, just to cover the whole arena and the spectrum of our topic. So with respect to scalability, yes, they are scalable. The more machines you add, the more performance you get, but it's not even. The more resources you put, you don't get equivalent performance. And that's a problem. So you're paying more for less performance. And at some point of time, when scalability reaches large scale, it starts to diminish. Most of the benchmarks you see online are done with respect to primitive operations. So they show you scalability. Yeah, we're scalable. Yes, you're scalable, but on primitive operations, not on the whole scale of the application. Another thing is shareability. You have kind of data coming from everywhere, different sources. This data comes from in different formats with different operation definitions, and this is another problem. Well, the main problem that we are concerned with here is the performance. The main problem here is that general purpose operating systems doesn't know about the application, that it's a data-oriented application. And it tries to deal with this process that manages data for big data or any bioinformatics application as a normal process. It tries to be fair to it, give it the time slice of the processor as other processes. It doesn't give it, of course, we can do priority, we can do all of this, but this is from the black box point of view. There's nothing special about a data management process. We have memory management overhead, because they are general purpose. Basically what we mean by multiple address space is that we have different processes and we have memory segments for every process, and switching between them is an overhead. Flushing the cache and the TLBs, table look aside buffers, this is an overhead. And basically page displacement algorithms for memory are designed for general purpose use. Scheduling overhead, of course, preemptive versus non-preemptive, which one we use. And the timer that we talked about, it consumes about 40% an overhead from the CPU time. Of course, this is good for interactive applications because you're switching between applications very quickly that give the illusion of concurrency on a single processor. But the whole idea here, for data management processes, the crunch data, this will waste a lot of time because you don't need to switch in the first place. And the execution stack that we talked about because of interoperability and all these nice features of current operating. So our proposed solution, what is the solution for that? What we need to do is to have a specific purpose operating systems for data mining and data applications and big data. So our proposed solution is asymmetric. asymmetric, core-based kernel that can be designed or that can handle big data operations in an optimum way. In this scheme, we have two design decisions. Basically, the first thing, partial tick list capability. So we need to switch off the timers at least on some processors. We don't need the timer on all processors. Because some processors are scheduling processors, this needs the timer, but other processors doesn't need the timer. In SMP, you apply the timer to every processor. The second thing is task-oriented dedicated cores. We need to dedicate data tasks to the cores. And in that sense, cores will be concentrating on the data crunching task instead of switching back and forth and doing I/O. We need to lower and narrow the stack. We need to build our interfaces very close to the hardware in this specific purpose operating system. Markup representation, of course, whenever possible to be interoperable and utilize virtualization as much as possible. So this is kind of a suggested architecture where here, now, the building block of our operating system or our environment is a core, not a node anymore. So in distributed systems, nodes are the building blocks. But here, we design it for the core to be the building block. The core is a standalone entity by itself and can run different types of kernels within the same environment for different functionalities. And we built this on a markup interpreter where all the big data threads running within the core are thread-based, not process-based. And this will reduce the overhead of switching between them. We have a single address space, so we're not switching the address space between threads. This is hectic. If you just have a single address space, this will get you considerable amount of performance and some dedicated disk. So in a distributed environment or a distributed architecture, this is how it will look like. We need cores to talk to each other, send messages to each other to be able to collaborate on some common problem. And in that case, cores can talk to each other when they are on the same node or in the same computer. But if we're building a distributed system, we need somehow a mechanism where remote cores can talk to each other. And we need to do that at the same time as the programmer is writing this kind of code of communication without the knowledge of the underlying environment. We need to do it transparently. So sending a message should not entail to the programmer whether this will go on the network or will go on the internal bus. So we built a protocol, a very low-level protocol that is being multiplexed by the kernel, by our new kernel, to make different cores communicate together. And this is kind of an architecture diagram that shows how cores physically will talk to each other. Usually you have core packages within your nodes, and every core package has what we call a BSP, bootstrap processor. This is the main processor, and there are APs, which are the application processors. So we need some sort of a topology to reduce the traffic between the different packages, whereby every group of application processors are managed by a BSP, and BSPs communicate together outside the package. So, guess what? We build a prototype for that. We have a prototype of such kernel. Very minimal, small prototype, but it's working. And we wanted to test the effect of running big data applications on it. So we chose the TerraSort benchmark. TerraSort benchmark is a very well-known benchmark that is used in this arena to actually assess the efficiency of big data algorithms and big data underlying environment. And it is targeting sorting a very large amount of data. And usually it is implemented in a MapReduce mechanism, so we adopted the same mechanism to be able to be compatible with our peers that we're going to experiment with. But the most important thing here is that in MapReduce application and in big data applications, the building unit is a node. Here, the building unit is a core. So every core can be a mapper or a reducer. We have management cores. So management cores will have the timer set up because they are management cores and need to do scheduling tasks. But the worker cores will be dedicated, uninterruptible. So they will get more performance. We ran this on our AMP kernel that we have a prototype for, and we were able to get 3x speed up over Hadoop, MapReduce, and Spark for sorting 10 gigabytes. Of course, we didn't have the enough environment to sort the 1 terabyte, but we compared both on the same condition. The main the main reason why we get this, or why we got those results, is disabling the timers on the worker nodes, changing how the operating system works, dedicated cores for specific tasks, and the low-level inter-core communication layer that is actually reducing the communication stack instead of having 7 layers in the OSI model to 1 or 2 layers to be able for cores to communicate together. We're currently building an environment for sorting the 1 terabyte, but it will take time, but we are targeting that. So what is our next step now? We need to come back to the bioinformatics arena. Our next step is to build a heuristic BLAST-like sequence alignment and deploy it on our environment. Okay? And deploy it on an AMP kernel-based operating system that we develop and see how much gain we can get out compared to the normal alignment algorithm and products used like BLAST and BIOS. Sequence alignment is a complex problem by default. It's a computationally complex problem. It is O of n times n for optimal alignments, which actually not carried out usually in production. M is the size of the query, M is the size of the database. Those are huge. Those are huge data. Not really big data. They are not big data from the data point of view. But they are big data from the computation point of view. With the amount of data being added in this arena, we will hit a variable with the size of the data as well. Okay? But you can reduce this complexity through heuristics, but it's still complex. It's not an easy problem to solve. You need a lot of resources, you need a lot of computational power. Sequence alignment is a big data, at least for now, from the computational point of view. Okay? So, as we said, it will be big data from the storage point of view as well, but when we took below the petabyte, and we were not big data, terabyte and petabyte, we were not big data from the data perspective yet. So our approach, I'm finishing, so I'm concluding. So our distributed approach is basically depending on those design decisions. We are going to re-engineer the indexing of the database to be distributable by nature. We're going to assign portions of the database to different cores to run in parallel and distribute. And we're going to deploy no execution deadlines and polling instead of interrupts. So we're going to eliminate all types of timers whenever possible. And basically we're going to adopt a MapReduce-like architecture to be able to scale outside a single node. So we are working on it right now. We have implemented part of the prototype of the sequence alignment, and we have very promising results compared to BLAST and Diamond. Actually, BLAST is kind of the norm. It's kind of the old guy who is here or there all the time. So it's kind of our reference point. Also, Diamond is a newcomer, which is much faster with specific conditions for short reads, and we are getting comparable results, even better results so far. We're going to announce the results when we complete the prototype, but they are very promising. Thank you for your time.
First of all, thank you for this talk. I'm graduating from computer science at economics. So I was asking about the part when you talk that you're doing different cores to do the task.
Yes.
So at this point, you don't use the operating system, so there is no operating system.
We're building a new kernel that runs within a virtual machine on top of Unix or Linux.
Okay, so
the complete kernel bare metal is implemented from scratch with new services.
Okay, so you are building a new kernel for this course.
For this specific problem, we're not trying to compete with Linux, FreeBSD, Mac, Windows. If you consider Windows an operating system, that's fine. But we're not trying to compete with those. We're trying to build a specific purpose operating system for this specific data management task. So this is not a replacement for Unix or for operating system. It's a replacement for them within this specific domain. Thank you.
شكرا جزيلا للتوك الجميلة دي. أنا بس عايز أسأل سؤالين. السؤال الأولاني هل إن يعني في الكيرنل دوت استخدمتوا specific data mining techniques يعني هل ان انتوا عملتوا extension مثلا
No, this will be the application layer of the kernel. But the most important thing about the kernel is that it gives high priority for data operations. It knows, it is designed to cater on data operations. So it is designed initially to detect that this is data and perform to the maximum. But for example, you cannot build GUI on this kernel, for example. You cannot open a data sheet or a spreadsheet and update it on this kernel. It is designed for data operations only. So the applications that will be deployed like the TheraSort, and this will be developed for this kernel, and since they are data intensive, the kernel will be able to perform better than any other operating system in this specific domain.
انا كنت question هل انتوا استخدمتوا برضه specific query language ولا
No, this is in the application. I'm talking about the kernel. I'm updating. Again, so no one will misunderstand. We're updating the scheduling and the system calls and the APIs of the kernel level. So if we port those types of applications, they will perform better.
But you didn't do some
We have some prototypes, of course, to be able to do TerraSort, for example, but limited. Because, you know, for example, when Google, before developing or before launching Android, they thought about building a new general purpose operating system. And they evaluated this with $18 billion to build. So building a whole operating system with all its interface kind of it's kind of in a general purpose domain. It's kind of really needs a lot of resources. So we're not after that. Okay, but we're going to provide the APIs for other people to be able to build it. Okay.
طيب قلت في الابلكيشن انك هتقارن بالفلاس والدايناميك.
Yes.
اشمعنى اخترت الفلاس؟ الفلاس is approximate solution for data alignment.
Is what?
Flash.
Yes.
Algorithm is approximate solution. مش optimal exact. Optimal exact هيبقى
who is running optimal now?
لا مفيش لان ده سبب المشكله بتاعت السرعه. لكن لو حضرتك استعملت سميث ووترمان هيديك اوبتيمال اكزاكت سوليوشن. صح هيبقى ابطا بس هيحل لك المشكله دي. وحضرتك لو استعملت برضه السيستم او الكيرنل ده على FPGA او GPU هيديلك برضه السرعه اكتر.
No. We're not talking about GPUs here. GPUs have constraints for memory and for power. Okay. So GPUs are not our candidate. GPU will fit in other application profiles.
ممكن FPGA.
For big data, I anticipate that the CPU models will win. This is just my anticipation. It is more general, more generic, and eventually, I don't know if you heard about that or not. The AVX extension, which actually resembles some of the GPU applications or GPU instructions, is now implemented in Intel, and it's growing. So AVX 512, whereby you can do array vectorization and array operations in parallel on 64 elements concurrently per core, is available and running. So GPU is not our candidate. But for Waltersmith, still you can build Waltersmith on that, but we don't have a reference point. That's why we're using something that we can compare with. We want. Look, there is a conflict of interest here. I'm not a bioinformatics guy. I'm a computer science guy. But this problem is just a candidate for me. It's just an appealing candidate. So I don't care about which application. All what I care about is that I can compare. I can run a query on Blast or Diamond, and I can run the exact query on the same configuration on my environment and compare them and say, I'm faster. So if there is someone who wants to implement Waltersmith, please, you're more than welcome. Okay.
Let's go for the presentation and try the new way of presentation. So I like your enthusiasm and how to present things. Even I couldn't catch some of your terminology in the presentation. So the configuration you are trying to reach at the end. As you mentioned, you are a computer guy. You are not a bioinformatician, right?
Yes.
So do you consider the changes that's happening in the future, like machine language, the speed of coding data, and when you are trying to implement that profile, or just do you have an idea that you are trying to establish?
That's exactly what we're doing. If we were to go on the application front or the middleware front, then we had to care about this. But what we are doing is something at the core that will speed up everything. So if you do that at the core, anything that you develop at the application layer will still run faster. So I'm not really caring much about new trends and developments, something like that, but I'm caring about that the core. The reference point is not optimal with respect to data. Those operating systems that we are using data operations are not optimal. This is the research question. Whatever you can develop on top of the normal general purpose operating system in the domain of data management, you will be able to develop it on my operating or the new operating system. And the key challenge here is that we are faster without changing the algorithm. Okay?
حابب حضرتك كتير جدا على البرزنتيشن، بس كان عندي سؤال لو سمحت. البارallel كومبيوتنج لو استخدمت اكتر من ماشين عليهم كلهم نفس الكيرنل، هل الكوميونيكيشن بين الكيرنلز كلها المختلفه ده هيأثر عندي في البرفورمانس؟
In my position or
your kernel.
the new kernel, it will not, because what I have done here is that I have minimized the stack. So what we have done here is that, so here we minimize the network stack for the core communication. And this network stack allows different boards on different machines to communicate directly without going into the operating system stack that we described earlier. So it will be definitely faster. And this is one of the key points that we are capitalizing on. So here, when we talk about general purpose operating systems, this is a traditional Unix stack. It's huge. You need to go through all of this, from the application layer until the network part, to be able to send a single message back and forth. So, no, in our case, we're solving this. We're narrowing the stack, compacting the stack. We're definitely going to build a similar stack for normal TCP/IP communication and